Alright, so let's try the exact same process on the next function, which is x to the fourth minus 4x cubed plus 5. Again, we want to determine anything we can about this graph. This is a polynomial function. So what's the domain of this graph? Again, I just said it's a polynomial function. And if it's a polynomial function, we know that the domain is going to be negative infinity to infinity. Next thing we would do is try to find the x-intercepts of this graph. But if you think about it, an x-intercept is where the function is equal to 0, right? And if you set this function equal to 0, x to the fourth minus 4x cubed plus 5 equal to 0, there's no tricks to solve this problem like there was in the previous problem where we could do factoring. There's no u substitution here. So this one literally would require the rational zeros theorem. And the rational zeros theorem is a huge pain in the butt. We don't even know if there's rational zeros. That would just tell us if it's a rational zero, what it would be. So the idea is let's just skip the x-intercepts in this problem. They're not easy. I wouldn't expect you to do them on the test. But what you always can do is a y-intercept. Again, a y-intercept's really easy because you just plug in x equals 0. So what's f of 0? In this case, it would be 0 to the fourth minus 4 times 0 cubed plus 5. So I'm getting the point 0 is my x value, plugged in 0. I got 5 out is my y value. So I'm getting a y-intercept of 0, 5. Okay, so that's all we can really glean from the first part of the problem. I mean, you might know some other things. For instance, this is an even polynomial with a positive leading coefficient. So you might know that this function starts high and ends high. That's not something that I'm expecting you to know. That's something you learned in college algebra, but I'm not expecting you to know that or note that here. I just need the domain and the y-intercept. To look at that's step 1. Now let's go into step 2 to find the intervals of increasing, decreasing, and relative extrema. To do that, we're going to be analyzing the first derivative of the function. Again, let's go ahead and write down that original function. F of x was, and I'm going to zoom out so I can see it. F of x is x to the fourth minus 4x cubed plus 5 is our function here. So that allows me to find the derivative of the function. The derivative of the function, well, the derivative of x to the fourth is 4x cubed. And the derivative of minus 4x cubed would be minus 4 times 3x squared, so that would be minus 12x squared. The derivative of 5, again, of course, is 0. We set this equal to 0 or undefined. It's a polynomial function, so this is never undefined. So this is where we are with the derivative. The derivative is 4x cubed minus 12x squared. We try to factor this out. I know I can take out a 4x squared in common. 4x cubed divided by 4x squared is x squared, or sorry, just x. And minus 12x squared divided by 4x squared would be a minus 3. We set that equal to 0. Set each of the factors equal to 0. 4x squared equal to 0. Divide by 4 and take the square root would give me x equals 0. X minus 3 equals 0. Add 3 to both sides would give me x equals 3. So these right here are my critical values because they are in the domain of the original function. Again, the original function being a polynomial, so it's defined at every single point. Okay, so let's continue. What do we do from that point on? From that point on, we need to create our number line. We break it up at those critical values, which was 0 and 3. We know our derivative at those critical values is 0. We look at the first interval, which would be negative infinity to 0. The second interval, which would be 0 to 3, and the third interval, which would be 3 to infinity. Why do we care about that? Because we need test points, and we need to plug that into the derivative. Again, the derivative factored was 4x squared times x minus 3. I need some number less than 0. How about negative 10? Some number between 0 and 3. How about the number 1? And some number bigger than 3. How about the number 10? I'm plugging these into the derivative, looking at the value of each factor. Negative 10 squared times 4, well, heck, anything squared times 4 is going to be positive, so I always know my first factor is positive. Negative 10 minus 3 is negative. A positive times a negative is negative, so because that test point was negative, that entire interval is negative. 1, again, when we plugged into the first one, you have to get positive. 1 minus 3 is negative. A positive times a negative is a negative, so that means I'm decreasing, well, sorry, that means because that test point was negative, all points are in that interval are negative. 10, again, the first one has to be positive, and then 10 minus 3 is also positive. A positive times a positive is positive. So since that test point was positive, that entire interval must be positive. Okay, why do I care about this? Again, because this tells me about my original function. Any place the original function, the derivative was negative, the original function has to be decreasing. And any place that the derivative was positive, the function has to be increasing. Again, changing from negative to negative, this is neither a max nor a min. Most likely that point right there is an inflection point, just to let you know. And then from the first derivative test when x equals 3, because I changed from decreasing to increasing, I know that point has to be a minimum. Well, that is a point on the graph, so I do want to actually find the value of that point. To find the value of that point, I need to throw it into the original function. The original function was x to the 4th minus 4x cubed plus 5. I'm plugging in the value 3, and I know whatever that gives me when I plug in 3, whatever my y value is, I know that point has to be a minimum. So I'm going to go into my calculator now, table feature, clear out what's in there. I'm going to do x raised to the 4th power, get out of the exponent, minus 4x cubed, and then I have that plus 5. Make sure you get out of the exponent on that. Start doesn't matter, step doesn't matter. Make sure you've selected ask x, hit enter for OK, type in the number 3, enter, and I'm getting negative 22. So that tells me the point 3, negative 22 is a minimum. So again, where's my function increasing? It increases when the derivative's positive. That was on the interval 3 to infinity. Whereas my function decreasing, it decreases anywhere the derivative was negative. This was actually on 2 intervals, and even though at 0, it seems that since I go from negative to negative, you can include it, but you cannot include it at x equals 0 because it is neither increasing nor decreasing at that point. It's decreasing to the left of it, it's decreasing to the right of it, but it is not decreasing at that point. So you would have to break this up, and you'd have to break it up as the first interval, which was negative infinity to 0. And then you'd also have to do the second interval, which is 0 to 3. Where was our maximum? We determined that there was no maximum for this problem. And the minimum, we found a minimum at 3, negative 22. So that's all the information from analyzing the original function. Couldn't get our x-intercepts, which is too bad, but that's fine. There's probably not a nice x-intercept. We were able to get that y-intercept. We know our increasing, decreasing, our max, there is none, and we know our minimum. And again, we are going to be using this number line. When we use that number line, we are going to be using that number line below the graph on the next page. So let's move on to step 3, which is analyzing the second derivative of the function.